Regularization. If I were to summarize this entire chapter in one line, it would be regularization is a technique to tune or calibrate your machine learning models from the pitfalls of overfitting, underfitting, and also getting the best values for your machine learning model parameters, which is to minimize the adjusted loss function. So regularization helps with a lot of things. So let's take an example of overfitting to understand this. Let's say you have data points for various mouse. You have weight and height, and you're trying to, from the independent variable weight, predict the dependent variable height. So what do? We've learned in chapter 2 we can use linear regression, right? So what do? We have test data set, and we could fit a linear line, or we can have a quadratic equation that we can fit. And very quickly we can see that this quadratic equation is an example of overfitting, whereas this line is not that example. So that's just one simplistic example of what overfitting is. Because if you fit too much, then if you get a data point that's outside, then this line actually does a better job of predicting the trend versus this quadratic equation. So overfitting is an important concept. Similarly, underfitting and not having the right model parameters is super important. Because if you just run a linear regression and you don't have the best parameters, or if you fit too much or if you fit too less, then your model is not as accurate as it could be. So that's what we're going to learn. Various techniques. This chapter has like 7 different algorithms that it shares as to how we can use regularization to fix overfitting, underfitting, and getting the best values for your parameters, right? So in this video, there's 2 parts to chapter 3. This is part 1 of chapter 3. I'm going to cover these 4 areas. Introduction to what is bias, what is variance, what's overfitting, go in depth of what we just talked about, and how regularization helps with fixing that. We'll look at 2 algorithms, k-fold out of sample validation, which is algorithm 4. So far we've covered 3 algorithms in the previous chapters, and then forward stepwise regression, which is algorithm 5. And then we'll talk about this problem of instability and how with penalty functions, regularization helps with solving that problem of instability. In part 2 of the video, we will cover the remaining 5 algorithms. Lasso, k-fold cross-validation with lasso, concept of information criteria. We'll talk about AIC, BIC, and the 9th algorithm, parametric bootstrap, and lasso confidence interval, and subsampling, the 10th one. So let's get into chapter 3, part 1, right? Bias, variance, overfitting, regularization. These are all related concepts. So let's get into it. So we just briefly in the introduction shared as to what is overfitting, right? But in a sense, a machine learning model is considered to overfit when our machine learning model does a very good job capturing the relationship in the training set with low bias, but does not do well in predicting the testing set because it has high variance. So if we see low bias in training set and high variance in testing set, then we say that our model is overfit. In simplistic term, I'm greatly simplifying this, but that's the intuition. So then we need to now understand what is bias, what is variance, and then eventually, okay, if it is low bias in training, high variance in testing, then I understand it's overfit. So let's understand what is bias. So bias, we say that our algorithm is having high bias if it has the inability to capture the true relationship between the dependent variable y and independent variable x. So using independent variables, we are predicting the dependent variable. So in the training data set, if it cannot capture the true relationship, then we say it has high bias, right? So high bias is bad, because if it can't even capture in the training data set what X predicts what Y, in this case weight predicting height, then we say it has high bias. It cannot learn, it has not learned enough from the training data set. Variance is on the testing data set. So it's the difference between the machine learning model training data set and testing data set. So we can say that variance is the outcome of when you take the model that you've trained in your training data set and you apply it to a testing data set, which is a new data set. And if you see high variance, meaning inability to predict, and there's a difference between true value and the predicted value, then it has high variance, meaning in real life it cannot perform. So then it is high variance. So what do you need? You want low bias and low variance, but can they come together? That's the trick. So finding that sweet spot of getting optimum low bias and low variations is the technique of regularization, right? So regularization, these algorithms that we will get into, helps the machine learning model so that it doesn't overfit, right? It doesn't overfit. And regularization is just one such set of techniques. There is also a boosting technique, there's bagging technique, not covered in this chapter, that are also used for solving overfitting. But in a sense, if there's high bias in training data set and high variance in testing data set, then there is, let's say there's high bias, low bias in training data set, but high variance in testing data set, then it is overfit, meaning you're able to capture everything in the training, but in real life, when you're put on a testing data set, your model fails, then it is considered overfit. And regularization helps with finding that sweet spot. So that's the high level of these concepts. So now let's look into a specific algorithm called k-fold out of sample validation. So the algorithm has 3 steps. The first step is you take your data set and you split that data into k bins, equal bins. Let's say it could be 10-fold out of sample validation. Then there are 10 bins. And let's say you have 100 data points. So then each data point has equal data in each of these 10 bins. So each of the 10 bins have 10 data points, right? So you split data randomly but evenly in each of these k bins. Once you do that, you train your algorithm using k minus 1 bin. So let's say you have 10 bins. In the 9 bins, 90 data points you use for training. And then 1 bin, the kth bin, you keep for testing. So you train on the 9 and test on the 10th, let's say. And then you check what is the R squared, right? Which is basically, if you remember from the last chapter, it explains what independent variable, what percentage of independent variable explains the prediction, right, of the dependent variable. That's R squared. So you do that for the kth bin, and then you shift that. So you do it for every bin. So first you start with the first bin as the testing data set, then you calculate the R squared, then you do the second bin as the testing data set, and then everyone else is the training data set. Then you keep calculating R squared for all of these 10 times if it is 10-fold. And then you keep repeating, and you get all of the R squared. And then you take the average of the R squared of those, let's say, 10 bins. And that is a better predictor of what is your machine learning model's prediction capability. So in a sense, this helps you not take one specific R squared for one bin, but you average it out. And there's one other pro tip. So in this, what we did is we cheated a little bit because we used all the data points eventually as part of training data set. But what we could do is we just take one bin out and never train on it. We do, let's say we had 10 bins. The first bin, we take out the first 10 data points. And then we do 9-fold out of sample validation. And then we do the R squared. And then we calculate the R squared on the bin that was never touched, the holy bin, right? And then whatever that R squared is, maybe that's what we look at. It's the out of sample R squared. So that's OOSR 2. So out of sample R squared. So that's k-fold out of sample validation algorithm. Simple, 3 steps. Split it into bins, calculate for every bin R squared, average it out, and then you have your combined average R squared that you can use for your algorithm. There's another greedy approach called a forward stepwise regression. In this, what you do is, there may be times when you have like hundreds of explanatory variables or independent variables that predict your dependent variable. So how do you quickly get which of those variables are the most impactful? Like with the least number of X variables, how can you most get the best prediction in Y? That is the solution forward stepwise regression provides. It helps us very quickly to find out which of these independent variables have the maximum prediction power. So what are the steps? First, you run your multiple regression with all the explanatory variables, and then find out which of these variables have the highest absolute t-value and whose p-value is significant, less than 0.05. And that becomes your first variable that has the highest prediction power. And then what you do is you never remove it. And then you run the regression, multiple regression, with the second variable. And when you do that for the second variable, what you do is you find out how to now add the second variable and repeat. So first variable is there, and then the second variable is part of it. Then find out which of the combination of variable 1 plus variable 2, variable 1 plus variable 3, variable 1 plus variable 4, which of those two combinations have the highest t-value and is still significant. Then you add that second variable. And you keep adding variables until your p-value is significant. And you can use as guardrails, R squared should be improving, adjusted R squared should be improving, and you continue to get lower AIC and BIC values. These are your goodness of fit measures. So very quickly you can get combinations of variables that will help you predict with the least number of variables, highest prediction power. There's this one issue of instability, which is important as we solve for overfitting. So based on the training data set that we used, the prediction or the coefficient of your variables could be very different. It could change drastically. And so these fitted models, as we saw in the k-fold validations, we are using different training testing data set. And so the quality of your out of sample performance will differ drastically based on what you train on and what you test on. So that is the problem of instability. Like if I were to just pick this k-1th bucket for testing, now it is different number, and then it's very different if I were to pick the k-2 bucket. And if I were to pick in forward stepwise regression 69 versus 68 variables, it could be significantly different. So that's a big problem. Like you've done so much work and you don't know when your algorithm becomes unstable. So that's where regularization techniques help solve for that. And the way they do it is with a very genius mechanism. Like let's say in the linear regression, we minimize least squared, right? The sum of least squared distances or the residuals from the predicted line to your training data set. What they do is they add this concept of penalty. So they minimize not just the deviance or the residuals, but they minimize the penalty plus the residuals, right? So they minimize penalized deviance, right? So they have this penalty functions that they use, and you can use lasso, which is the default one. There you can use ridge regression, you can use elastic net, and there's also log. So you can use penalty functions on top of your residuals that make your prediction better, because it's not going to make it overfit, because it's adding some random penalty on top of the residuals. So your algorithms becomes much more stable, because it's trained now to also handle this penalty that gets added, and there's different types of penalty functions. So that's part one of this video. In the next video, we will cover 5 remaining algorithms that we didn't get to. But in a sense, we get this, right? We have instability in our algorithms. We don't know which variables to choose, how many variables to choose. We don't know what data set to test on and train on. How do we solve for all of that? How do we know if it's overfit, underfit? At least we got to know if our linear regression model is better, multiple regression model is better or not, how to test for it. So that's the key set of concepts, the intuitive concepts. It's highly simplified, but at least we get the intuition behind this. And then we'll get into the algorithms in the next video. Yeah. Thanks.